It is our pleasure to welcome you to the Hong Kong Institute for Advanced Study Distinguished Lecture. May we invite Professor Zheng Wang, the Associate Vice President of Strategic Research of City University of Hong Kong, to come to the stage for introduction. Professor Wang.
Thank you. Good afternoon, Professor Leons, Mr. Cabot, President Boy, distinguished guests, colleagues, students, academic friends, ladies and gentlemen. I'm honored to be the facilitator of today's lecture, and I extend a heartfelt welcome to all of you attending HKIAS Distinguished Lecture. I'm truly privileged and delighted to have Professor Pierre-Louis Leons, our esteemed HKIAS Senior Fellow, as our distinguished speaker today. Professor Leons holds a prestigious position at the Collège de France and many other distinguished titles. He is a member of the Académie Européenne, a member of the French Academy of Science, and a recipient of the Fields Medal in 1994. The lecture Professor Leons will deliver today, titled "On Some New Mathematical Models and Their Applications," promises to immerse us in the beauty of mathematics. I also want to thank Professor Leons for gracing us with his talk at our just concluded HKIAS International Conference on Mathematical Analysis and its Applications, held over the past 2 days at the CTU Hong Kong. We had the honor of hosting numerous world-renowned mathematicians to share their valuable expertise and insights. Professor Leons was among these distinguished speakers. Lastly, I would like to express our gratitude to all conference speakers who extended their stay for an additional day to attend Professor Leons' talk. Once again, thank you all for your warm support and enthusiastic participation. So, may I now invite President Professor Freddie Boy to deliver the opening speech. Professor Boy, please.
First of all, we are very glad Council General Cabot can make it finally, the infamous Hong Kong traffic jam. Sometimes better to walk than to drive. It's our great honor today to have such an exceptional, outstanding speaker. And I'm so delighted that our Professor Pierre-Louis is willing to able to come to visit us. I had the privilege of having a Chinese dinner with him in Paris, and really got to know him as a colleague and a friend. It's so wonderful. And I'm also delighted that we, in Hong Kong in general and CDU in particular, has been able to connect with France. I just came back from a trip in Paris where we have met a good number of very distinguished academicians, and I can tell you that we have a lot to learn from the French way of education. And one of the things I do observe is that they're strongly entrenched in this mathematics, basic physics, and so on. And though we are focusing on technology and engineering, to be truly creative, to be able to be deeply curious, these are the things and disciplines that we should not put light weights to. And so CDU wants to be a really good university for the sake of our students, and therefore I'm also delighted to see that all these faces are very young, including those who are old but looks very young. So make you happy. And that's very important because the contribution here is that we hope that such a distinguished lecture hope to inspire you. It's all right if you don't understand everything. I never do. But it's all right to feel excited and inspiring, being inspired. That's the most important thing, because that will drive you to learn much more than you would ever before. So I won't stand in the way of the lecture. I just want to thank again Professor Leon for coming and giving us this privilege. Thank you.
Thank you, Professor Boy, for your inspiring words. And now I would like to invite Mr. Benjamin Cabolet, Consul for Culture, Science and Education, Consulate General of France in Hong Kong and Macau, to come to the stage to give the opening speech. Mr. Cabolet, please.
Thank you so much. And first of all, apologies for being late. It's just last minute, but sorry for leaving you waiting. First of all, I want to thank you, President Boy, dear Professor Lyons, Professor Sarlet, ladies and gentlemen. I want to thank the City University and its president for welcoming us one more time for here in the beautiful university for a distinguished lecture. I think today we are really witnessing once more a great example of a successful cooperation between very high-level Hong Kong and French institutions. It's a great pleasure to be with you today to of course, hear about this the work of Professor Lyon, but in general, you know, to be in his presence. Field medalist, you mentioned it, Professor at Collège de France, which in France is really a name that resonates for many people and in terms of excellence. Your work, Professor, has not only advanced the field of mathematics, but has also fostered collaboration and knowledge exchange between our two regions, France, Asia, but not only, of course. You have dedicated your career to the study of, and I'm sorry I'm going to use a big word that I don't understand myself, I say thank you, Professor Boy, for mentioning it, but non-linear partial differential equation and their application, and I think this aspect is very important. Your groundbreaking research have had a profound impact on various fields, ranging from fluid mechanics to mathematical physics, image processing and finance, and you have provided invaluable insight and solution to complex problems that have practical implication in our daily life, and I think it's a very important aspect. One of the most significant aspects of your work, Professor Lyons, is your emphasis on interdisciplinary collaborations. You recognize that the challenge we face today requires this approach, multidisciplinary, and you brought together different experts from different fields to tackle complex problems. And you've been a strong advocate, and you still are, of course, of collaboration, both within mathematics, but also across other scientific disciplines. Your work has paved the way for fruitful collaboration between mathematicians, physicists, engineers, economists, among others. In the context of the French and Hong Kong scientific cooperation, your contribution is particularly noteworthy. France has a long-standing tradition of excellence in mathematics, and Hong Kong has emerged as a vibrant scientific hub in Asia. And by fostering collaboration between those two regions, we can leverage each other's strengths, create synergy, and lead, hopefully, to groundbreaking discoveries and innovation. I would like to take this opportunity also to commend Professor Sylvie Méléard, who is also in Hong Kong and who has participated in HKIAS International Conference on Mathematical Analysis and its application. We are really honored to have not one but two great French mathematicians in Hong Kong. So I really wish you enjoyable conference. Thank you so much, and yeah, enjoy the conference. Thank you.
Thank you, Mr. Kobo. Please remain on stage. May we now invite our speaker, Professor Lyons, President Boye, the lecture organizer, Professor Charlet, the lecture facilitator, Professor Zheng Wang, Dean of College of Science, Professor Xing Wang, and Dean of College of Engineering, Professor Jian Lu, to come to the stage for a group photo, please. Thank you all. Please be seated. We will also take a group photo with all the participants at the end of the lecture. May we now invite Professor Lyons to deliver the Hong Kong Institute for Advanced Study Distinguished Lecture. Professor Lyons, please.
seems to be working. Yes, it does. Well, thank you for coming tonight. After all, to hear mathematicians is always taking a risk, right? But I promise to be, well, to avoid as much technical math as possible. In fact, I think, okay, I think there would be only two formulas maybe in the whole talk. Doesn't mean that it's going to be any easier, but anyway, there won't be too many mathematical formulas. But first, before I start discussing what I would like to discuss today, I really want to thank CPU. I see in the audience all the speakers of the workshop that was held this week. It was a fun week. Huh? It was an excellent workshop. The hospitality was amazing, and we really enjoyed it very much. So tonight I want to say a few words about, indeed, some topics that I've been involved with for the last 20 years. But I'll begin with some general considerations about math, and before getting into a more precise subject. So those general considerations, which are standard for many mathematicians, and I apologize for my colleagues in the audience, because those are things they might know very well. Then I will spend some time discussing, and the major part of the talk is going to be about main-field games, and there will be a 5 minutes intersection with my previous talk in the workshop about large random matrices. Why am I choosing those two topics? It's because we will see this type of back and forth travel between real-world applications requiring new mathematical objects, theories, and also problems, which indeed lead to the creation of new mathematical tools, which in turn can be used to study different applications. So it's not a one-way street between applications and mathematics. It goes back and forth with all kinds of feedback loops that I want to illustrate today, and I'll be more precise later on. Okay. Let me begin. So I just said that I'm going to make some vague general statements about math. Is anyone allowed to do it? And the answer is no. And I'm going to prove it. That's going to be the only theorem I prove today. Von Neumann, which is clearly one of my heroes, in fact, my hero, period. Von Neumann, for the young people, they may have heard of him. Von Neumann started in logic, in mathematics, in logic and group theory. Later on, invented one of the mathematical formulations of quantum mechanics, namely the von Neumann algebras. He invented ergodic theory. He invented game theory. He was working as a consultant on fluid and gas dynamics problems. Peter Lachs always said in his, another great mathematician, always said in his lecture that von Neumann couldn't solve the fluid mechanics equation, so he invented computers. Okay? And indeed, the invention of computers, that's a little bit simplified, but he really clearly simplifies the logic and the organization of modern-day computers. In fact, we are still talking about the von Neumann machines And essentially, all our computers are von Neumann machines. Anyway, so later on, he discovered cellular automata, and he was interested in so many questions. He had an eidetic memory. So typically, you would ask him, you would tell the title of a book, and he would start from line 1. Usually his guest would say, okay, after page 100, that's enough. Anyway, he just knew everything he was reading about. So you see the kind of monster I'm discussing. Von Neumann, in the late 20s, was asked, how much math do you know? He immediately answered. He was always answering immediately all questions because he had already thought about the question before. He immediately answered 28%. Okay, so of course 28, the precision is a joke. But you see someone like von Neumann, probably the greatest mathematicians ever, in my eyes, in the late 20s, 1920s, saying, well, he didn't claim he knew more than roughly a quarter of mathematics. So since then, that was a century ago, and it was von Neumann. So take any mathematician, well, he will know just a tiny bit of mathematics. They have some vague understanding of a greater part. So this is why whenever mathematicians make general observations about mathematics, you may say, but what does he know? So I'm going to try nevertheless, but I just wanted to warn you that I know little, and so my remarks might be completely stupid. But a few friends share the same remarks. In fact, von Neumann made another observation that I like very much. He said, one never understands mathematics, one gets used to it. Okay? Which is an interesting statement. But again, von Neumann is saying one never understands mathematics. So if some of you in the audience may have some difficulties from time to time to answer some parts, some mathematical notion, it's okay. One needs time to get used to it. Don't worry. Okay, so this being said, as I mentioned, I'm still going to try to make a few general comments. As is well known, math is now a science. There was, endless debates about is math a science or not. I think now it's over because things have changed a lot, especially because of the computer experiment. So it's a science, but it's also a language, okay? Both spoken and written. In fact, I tried to make an estimate, saying that, how can you decide if someone speaks a language or not? So it's about knowing like 200 to 300 words. So I'm not talking about being completely proficient in the language, but it's an order of magnitude. So 200 or 300 words, symbols in mathematics. And I got a rough number, it's a rough estimate, which makes mathematics the third most spoken language in the world. English comes first, Mandarin is second, and mathematics is third, much higher than Spanish, for instance. This is which is extremely, which is spoken by about 300 million people, so 400 million people. So that's, it shows that it is indeed a language which is not the property of mathematicians, which is shared by a huge community. So people always say a universal language. Okay, it is true that the notations are absolutely universal because you don't require any kind of translation for the notation. But still, a language spoken, third most spoken language. Many of my colleagues usually say, well, there are maths all over the place. Okay, I will give examples later on. But many mathematicians say, well, but there is the famous fundamental unity of mathematics. Okay? In fact, I'm not sure that the unity of mathematics reflects anything else than the unity of our brain. Okay, now I have to confess, I, like many mathematicians, I am not at all, I do not agree at all with the 5 different classes of Platonism in maths. Okay, so there are 4 or 5 different currents in philosophy of maths, which wouldn't accept what I'm saying, and I'm sure many mathematicians in the audience share this feeling, is that mathematics is a creation of our brain. Okay? So that's a conviction, nothing can be proved, but certainly that's my conviction, so you know where I stand. It's not so much about trying to define the truth, but to know where the speaker stands. A few elements of proof comes from etymology. If you take the main branches of mathematics and you look at the words. So let's begin, calculus. Many young faces, you have learned calculus. People tend to forget that calculus comes from Latin and means what it means. It means a pebble. In fact, this meaning has remained in medicine, where a kidney stone is called a calculus, and in French, in Spanish, in Italian, calcolo means also a kidney stone, because that's the original signification. And in fact, indeed, one was using stones to count, okay? And hence the calculus. Geometry, Greek, 2 words, ground, geo, that's geophysics, geology, geo, that's the ground. Metry is about measuring, okay? So, and that's another big branch. Algebra is a different story. Analysis is interesting. It also comes from Latin, and it corresponds, there is this idea of trying to cut into little pieces before trying to assemble it to get a better global understanding. And that's exactly what we try to achieve in mathematical analysis, but think also of psychotherapy and analysis in that sense, in the psychological sense. Hazard, alia. Okay, hazard is an Arabic word, which means dice. Okay, doesn't mean randomness, probability, and so on. It meant dice. Alia is the same. So alia is Latin. It's more. It's more used in the Roman languages. And again, alia jactaes. You may remember the famous sentence, dice. Okay, and progressively for alia, which is present in aléatoire and so on, the meaning, the fact that it meant dice was transformed in the way you are throwing the dice, in the science of throwing dice, and it became essentially aléatoire, which is the basic object in probability theory. Okay, so by this I just want to illustrate that if you take 3 or 4 branches of mathematics, they all come from observing reality and trying to use some kind of concepts like numbers, shapes, forms, and so on, strange random results, and requiring what mathematics do, which is taking one step back into abstractness, if you want to say so. Okay, so the things that I'm particularly interested, which are related to equations, differential equations, of course, began with Newton, the famous F equal m gamma. Gamma is a double derivative, the acceleration. You differentiate twice in time. Of course, no one knew what differentiating meant at that time. Okay, so he had this intuition of fluxion, which is in fact an idea about what a probability could be. Anyway, so in the 19th century, equations were used more and more. I cannot resist this quote by Alan Turing, the famous, another inventor of computer science, that sent a postcard once to one of his friends, and said, well, the universe is a big differential equation. And he had lots of humor, and he added, and God is the initial condition. So this is clearly where my field started to expand, 19th century, and by the end of the 19th century, one started to make distinctions, and even more so in the 20th century, a distinction between pure and applied. First, I resent the word that if you are interested in applied mathematics, you're not pure, so you're impure, right? So that's not okay. Plus, there's lots of pure activities in applied mathematics, so it doesn't make any sense. So in the end, I'm not kind of really concerned about such distinctions, although I would prefer to replace pure by theoretical, but that's not good enough because there are also theoretical maths in applied. But I would certainly, what I'm advocating is classical maths, while applied could be seen in view of the history as just maths or modern maths. Anyway, so 19th century, 20th century, the rise of partial differential equations, and of course we have been entering for now half a century, for more than half a century, in a numerical era. People say digital era. I don't like the word digital, it's really numerical. And so this is why there is mathematics all over the place, and if you don't like maths, too bad, because it's not going to get any better. It's going to get only worse. More and more maths all over the place, and we know that nowadays with the famous algorithms, which are more and more governing our lives. So this is, and one might think that this is a natural process. I mean, our brain is probably has a tendency to go always to more abstraction. It's very interesting to compare various activities, human activities, in particular the story of money and how it's becoming more and more abstract across the centuries. But anyway, so we are facing this, and after all this thing, what I want to advocate is not so much that it's a theoretical math against applications and so on. This, I don't care about this distinction. In the end, as I think most of us would agree, it's a matter of not what you do, but the question of the mindset, being interested not only in maths. So what I'm going to do today is just an illustration, taking examples that I know because I work on them, otherwise I know nothing. Remember my warning. My initial warning at von Neumann. So I'm not claiming they are particularly important. I just know those. Two examples of the feedback loops that exist between mathematical theory, or my branch of mathematical theory, namely analysis. In fact, when I say my, I should say our, thinking of the workshop we had this week. Modeling and application. So applications, as I said, requiring the creation. Creation is a big word. Quite often, there has been already some ideas about creating some object, and mathematicians create a synthesis of those objects and create a concept out of these ideas. Creation, synthesis of new mathematical objects that allow to model new situations and applications, which require new mathematical theories that allow to study new applied topics and so on. So this is, it's going back and forth all the time, and that's what we, people that are interested in applied mathematics are in. So today, I'm going to mention things about min-field games. Why did we stumble upon this theory of min-field games? Well, you see DD and an arrow. DD, that's développement durable in French, which means sustainable development. About 20 years ago, we began an initiative entirely subsidized by two private companies, namely Crédit Agricole, one of the major banks which is very much associated to agriculture in France, and the French electricity company. And we are talking about 2004. We decided to create a research initiative which would be on finance and sustainable development. In the early 2000s, basically, everybody interested in sustainable development thought that finance was the enemy. We thought differently because we thought in the end, if we really want to be efficient, it will require economical and financial tools in order to really improve the situation. Okay, this being said, that's a research initiative. Honestly, we didn't know exactly where we were going and what would be the role of math. Quite rapidly, we realized that there are certain differences in situations which are related to the future of the planet and sustainable development in particular, which is the fact that one is dealing with a long horizon. Horizon is long. It's not about trying to understand a system for the next 20 minutes, next hour, next day, or predicting weather tomorrow, right? It's long horizon. Many actors. You cannot say, okay, I'm going to change the situation. No way. Okay? It's many actors. And for each actor, the other actors play an important role. In economics, that's called externalities, because this means that one agent has to take into account the externalities, which are what the other agents are doing. Okay, so we realized that one needed to try to build some kind of mathematical theory to tackle such situations. Okay, and that's what I'm going to illustrate. I'll show you an applications. In doing so, as we will see later on, we needed to write down equations set in infinite dimensional spaces. Don't worry. Essentially, equation set either in the space of measures or the space of variety measures, and how to solve equations. Usually when you take physical equations, mechanical equations, fluid equations, they are set in the physical space, okay? 3 dimensions plus possibly time. Here, they were set in a totally different object, so clearly trying to create the branch of PDEs, but set in a very different space. Once this was done, people soon realized that one could then study other problems which are set on the space of variety measures, which have other applications. Optimal control of PDEs, large random matrices, and so on. Okay, so side remark that I won't that I cannot comment today is that when you make mathematical models, you can try to analyze them, cut into little pieces to understand, and then trying to build a global image. That's the etymology of analysis. You can try that, but at the end of the day, when you're dealing with a practical application, you need to do computations. Forget about explicit solutions in general; they don't exist. So, making numerical computation in a space which is infinite dimensional is a bit heavy. Okay, and I don't have time to expand upon that, but neural nets, more than machine learning, are indeed helping a lot to solve, I mean, maybe not all problems, but quite a lot of problems that are set in such infinite dimensional spaces. So this is a more technical remark, forget it. Okay, min-field games. So I told you the context, sustainable development and finance, many actors, long term, lots of interactions. I need to go back a little back in time and to mention dynamic programming, the Bellman equation. That's the invention of Richard Bellman. By the way, Richard Bellman was a mathematical engineer. Mathematics doesn't belong to mathematicians. a mathematical engineer, and Peter Lax, the same, another of my heroes, always told me that he was a very close friend of Richard Bellman. This is the smartest guy I've ever seen. And when you know Peter Lax, which is not a dummy, this may really mean something. So in the 50s, Richard Bellman invented dynamic programming, which is a classic now in operational research, in management, in even computer science, and so on. And it's about decision theory, how to make the best possible decisions. Dynamic programming, Bellman. Okay, I'm among the people which are responsible for adding in front of Bellman, Hamilton and Jacobi, and so those are known. They are now known as Hamilton-Jacobi-Bellman equations, and even economists have changed their wording. Okay, what does dynamic programming and Bellman did? It's really trying to understand how to solve optimal decision problem, optimal control problem for a single agent. And there is this idea of recursive optimization going backward, but I don't want to say more. So what we tried to do was to say we don't have a player, we have a crowd of players, a huge amount of players. Each has to make decisions. Let's simplify by saying that we have only one population and that all the players react in similar ways. They are not the same, but they react in similar ways. And is it possible to write down self-consistent models for large populations of agent players, where each player makes its decision, taking into account the state of the population? His decisions affect the behavior of the crowd, which in turn affect the behavior of each agent. So this is a loop, and an equilibrium is just what the word means. Did we invent that? When I say we, it's with my, as mentioned a little bit below, that's with my old friend and collaborator Jean-Michel Lassay. Did we invent MFG? I don't know. Of course, that's what I said about creation versus synthesis. Of course, you find examples of such MFGs before. But there is one I want to mention, which is known as Psychohistory by Harry Seldon, 1951. In fact, you may not, okay, so I'm pausing because I want to see if someone realizes who is Harry Seldon. Okay? Harry Seldon is probably the name of a mathematician which has been mostly, which has been read by the most part of the world population. Harry Seldon, it doesn't exist. He's a fake. He's a literature character, and he was invented by Asimov in his Cycle Foundation, science fiction. And so Harry Seldon is indeed a mathematician. First volume of the Foundation, the first Foundation trilogy, so it's not that good. And recently, I think that Netflix has produced a series on Foundation. So you will see in that series, if you don't want to read the books, but I advise reading the books, you will see this character of Harry Seldon, and in fact also mathematicians. And but what Harry Seldon was supposed to say in his book is just amazing, because he says there is no way we can predict the behavior of an individual human being. But we can predict, and what we are trying to do with MFG is not predict, but explain the behavior of a crowd. He was indeed mentioning the law of large numbers explicitly, but he was also mentioning the fact about choosing, making decisions. Okay? It's not only saying, well, on the average, it has to happen. It was dynamical. So that's why, although we have not realized that some people said, oh, what you're trying to do is just psychohistory. Okay, indeed. So, okay, this is of course an anecdote, but there were quite a few particular examples in economics, and there's a celebrated paper in '96 by Crushels and Smith, two famous macroeconomists. I have no clue. I didn't know this paper, but Bob Lucas, Nobel Prize in Economics, that I will mention later on, maybe. Bob Lucas told me, you know, Pierre-Louis, what you're trying to do, this reminds me this paper of Crushel Smith, and we never understood this paper, maybe you can explain it to us. And in fact, this paper was not really setting up a theory of Milfield games. It was this paper was defining a game with a large population of agents. So this paper was just giving rules, no equations, just giving rules. So with possible economic shocks, what happens for every, in terms of the behavior of every agent. They didn't write the equation, and they had, but they designed a numerical procedure, which is quite amazing. With huge Monte Carlo simulations and so on, and they had a conclusion, which is to say, in the end, the only thing that matters is a single variable, and that 80 or 90% of the solution can be, the solution of this problem, not the equation, depends only on one variable. And I remember Lucas telling me, we disagree with that. It cannot be true. It has to depend on more properties of the population, and the mathematical theory clearly now allows us to completely understand that. But what I was saying is that indeed economists had the intuition, like physicists have the intuition of writing down partial differential equations and mathematical problems. They had the intuition of what later on came to be Milfield games. So the synthesis of those ideas, the terminology, the introduction of the infinite dimensional equation, and some of the main mathematical bricks, we were lucky enough to figure this out in the late 2000s. There has been an important development of the mathematical series. I would say there are 4 international workshops or meetings per year on that subject. Okay, honestly, that's too much. But numerical applications, multiple scientific communities, economics, finance, that's done, but also telecommunication. Okay? If you think about mobile telecommunications, it's full of Milfield games. People in computer science have been using it. Crowd motion is a nice application. Some physics teams have been working on some particular Milfield games models, which is something I like, because usually we mathematicians, and I, like many others, we work on equations written down by physicists a few years before, possibly half a century before, possibly even more. Okay? Now, at least once I was able to write down some equation that physicists would investigate. And in fact, they brought interesting ideas about phase transitions in those in Milfield games. There are groups, vaccination, energy transition is very much related to the original motivation, which was sustainable development, and also people in machine learning and AI, but that's a different style. What does it bring? So possibly it can be useful for applications. I should be the one judging. What about math? Does it bring anything new to math? Those are new problems. So in fact, you need to prove new theorems, fine, which is always a good activity for in terms of jobs at the end of the day. But what did it bring? If you forget completely applications, game, equilibrium, and so on, what it brought was really to do differential analysis, and not only moving points, like geodesics and so on, but really differentiating, really writing down equations on the space of measures or probability measures. Okay. And we will see that in the last few minutes of the lecture, we will see in indeed that this has applications in totally different problems. Okay, as you have clearly realized by now, I'm using lots of words. What is an MFG model? It might be time to try to describe the mathematical object. So what you require in order to create such a model is to say, okay, I'm a situation involving many agents, many something. First, you have to decide how you're going to describe mathematically the agent. Could be its age, its position. You have to decide its wealth. So that's the X, that's the state of the player. Clearly, you're addressing a crowd. So there is the issue that, if you have a few million individuals, it might be a little bit painful to collect all the information about each individual. So how to summarize that? Well, mathematically, there is an object which is the state of the population, which is, if the population, let's say, has size 1, which is the density, the probability density, the probability of corresponding to the population. So think that's like an histogram, okay? There are that many number of people in state 1, that many people in state 2, and so on. So you collect all those information. That's the state of the population. Next thing that you need to describe in order to make an FFG model is the interaction between an agent and the crowd. Okay? How does the state of the crowd affect what I'm willing to do? There is a selection of individual strategy. Okay, so how am I going to select? I know where the crowd, what the crowd is. How do I select my actions? And of course, in order to make a selection, usually you have to measure the efficiency of your choice. That's what is traditionally known in decision theory, in game theory, or in control theory as a value function. Okay? The cost function, if you want. So naturally, you are led, in the case of just one population, one single population, you're led to inquire about the efficiency is going to be measured by a function u that will depend on time. This is dynamical. That will depend on the variables you chose to describe the state of each agent, and m, which is, once you're given an x, then you have an m of x, which is the state of the population. Okay. Okay, don't look at the last slides, okay, because that's the precise math formulation in one very particular case. So that's really, I'm allowing a glance of the last equations only to mathematicians. The others shouldn't look at those equations, especially if you want to be able to sleep tonight. But anyway, so the master equation. So the master equation is an equation for the thing that measures the efficiency of the equilibrium. That's a u guy. It depends on time. That's du over dt. And just so that you have an idea, there are 3 blocks. D, T, M. D is for decision, T is for transport, and M is about randomness. I'm simplifying a little bit because there could be a little more. There can be more connections between the blocks. So clearly, D is a decision block where each individual decides knowing the state of the crowd. But it's a dynamical decision, so you think of the dynamic problem, knowing the state of the population. But once the agents have decided about what they are going to do, this affects the state of the population. Okay? So if it's about location, think of an example. There is a crowd moving. You're one of the agents of the crowd. You decide to go in that direction. So all people around you decide to make such moves. Well, then the state of the population changes. And then it leads to new decisions and so on. So transport, individual actions modify M. And M is that in many problems, you do have sources of randomness and noise. Okay, so this is very abstract. In the sense where there is not much mathematical meat when you write such an equation. A precise an example is given down below. But what I want to emphasize here, It's not so much the equation, but that's on P. Probability measures. It's an equation set on the set of probability measures. A nonlinear partial differential equation set on the space of probability measures. Okay. Okay. There are a few situations when you have where you have a reduction to finite dimension. Don't have time to go there. Okay. So we coined this word master equation. We introduced the master equation with Jean-Michel Lasserie in 2004-2005. Only in 2023 we were able to get a completely general proof showing that the master equation is well posed in extreme generality, which encompasses agent-based models, optimal transportation, and the classic augmented field games. I don't have so well posed in the sense that like differential systems, right? Dynamical system. There is a maximum time of interval until which you have unique solutions. In general, singularities appear, and it turns out that although there might be Laplacians, I mean, certain order operators, regularizing operator floating in the equation, forget that. It turned out that because we are dealing with an infinite-dimensional problem, the main aspect is hyperbolic. And that's why singularities appear, and in general, which create new questions about modeling and so on. I don't have time to go there. And in fact, the analysis was also made possible by changing the notion of equilibrium. You've seen that the equilibrium is being measured in terms of an efficiency function, the value function, and we realize that if one takes the derivative with respect to x of u, it's a new system, which is really a non-conservative hyperbolic system, which means an equilibrium of strategies, which is interesting, because in game theory there is this idea that defining an equilibrium in game theory through values like Nash points may not be a very good idea. That what really matters in the end is equilibrium for strategies. So it turns out that mathematically that made a difference. Okay, naturally you can ask yourself, but the infinite, that's mathematical. Because if I'm dealing with a population which is 2-3 million people, maybe more, still it's a finite number. When you say infinite, it's infinite. It's not finite, okay? Does it really make sense? So this is a justification by saying I'm going to take a finite size population and let the size of the population going to infinity. Do I recover the same model, the same equations? So clearly I have no time, and there are still many open questions, although as long as there is a regular proof, unique smooth solutions, indeed what I'm going to say is true. But the point that I want to make is that when an agent is a point x, and then suddenly you have n agents, n points in physical space, and suddenly I'm talking about a measure. What is the connection? The connection is clear, because saying that the agents are indistinguishable. You know, in a population, the fact that you're called Ciarlet or you're called Lyons is completely irrelevant about the future of the economy of the country, right? That's the indistinguishability, which means that when you look at endpoints like that, you're willing to make all kinds of permutation. It's the same thing. Okay? So mathematically, this means that we are taking the quotient space of Rd to the n by the permutation group. Okay? Just means that if I take 2 points, writing down x1 or x1, x2 or x2, x1 is the same. Okay? Invariant by permutation. So this is about space, and quotient space creates singularities, right? Okay, let me try to explain that with my ends. Let's take a square. So x1 is in 0, 1. x2 is in 0, 1. I'm taking 2 points in the square, and what I'm saying is that if the points are symmetrical with respect to the diagonal, they are the same. What I'm doing? I'm just folding the square along the diagonal. Okay, so I have the square, and suddenly I'm creating an object which is a triangle. In 3 dimensions, I'm folding again. So as dimension grows, I'm folding more and more. I'm creating corners all over the place. Okay? So, and clearly, writing down a sum, because a sum is commutative, so it's the order in which you write down the xi is completely irrelevant, is the same. So you realize that, well, let's look at the empirical measure, counting. That's an efficient way to take independently of the dimension of positions. And that's how measures appear. There is another point of view, which is to say, I can also think that I have a random variable which takes values xi with probability 1 over n. And all those point of views, in fact, can be reflected in the are reflected in the mathematical analysis of these infinite dimensional equations. Okay, so a practical example is the so-called Edmond model for the production and storage of energies, oil, gas, and so on. So what we wanted to have a simulator of all carbon-based energies. So this is a large team. Yves Ajou, Charles Bertucci, Jean-Michel Lasserie, Antoine Rostand. That's why it's called Edmond. Edmond Rostand, the authors of Cyrano Bergerac and so on. So Antoine Rostand is the CEO of a startup that Jean-Michel Morel knows well, which has been working hard to obtain data on storage. It turns out that, especially with oil, okay, you have producers, you have consumers, and there is also strategic storage. And that's absolutely crucial in the organization of the oil market. Okay, so that's for Rostand. José Schenkman is a well-known economist in Colombia. Okay, so I think someone was saying something about multidisciplinary activities and so on. You see there people working in totally different areas. Okay. I'm sorry about this is not very clear. I'm sorry, too many copies and so on. Okay, so I don't have time to go to, but you see that there is a big slope here. We call this the cliff. And so I don't have time to explain the model, to explain the assumptions and so on. But why were we interested in a model like that? We were interested in a model like that when you realize that a cartel like OPEC, independently of the price of oil, has, in terms of market share, its market share is very stable, staying between 40 and 45% over decades. Regularity in data. Okay, so which might mean that there is something taking place where there is some kind of equilibrium taking place. Okay, so basically we have one big player, which is a cartel. We have a crowd of small players, and another crowd, which is a crowd of arbitragists, which are storing oil. Okay, you model the type of behaviors and so on. You write down the equation, solve them, Yves Ajou solves them numerically, and you get pictures like that, and then you get worried. The first prediction was that from time to time there would be cliffs with the price falling down extremely violently, and so we went to consult experts, and they told us, oh, no, we know that, we observe it. Oof, that's not entirely stupid. Second prediction was even worse. With a very small probability, from time to time we were observing negative prices. Okay, you say that, you say, well, maybe it's because of the numerics, it's close to zero, it's getting negative, just errors. But so we were doing more refined computation. No, we were getting really, from time to time, negative prices. Okay, we got a little bit depressed because that was after 2 years of work. And this is not something that takes place overnight. And then, cliff, rare, but possible negative prices. And fortunately, that's the only good aspect of what happened, namely the COVID crisis. The COVID crisis, if you remember, in March 2020, people talked about an oil war, right, between Russia and, in March, really the real beginning of the COVID crisis, between Russia and OPEC. We were a little bit doubtful because it looked like the perfect strategy in terms of game theory for both players. But anyway, and suddenly, on March 20, so you see 2020, there was an article in Financial Times quoting our paper. I had no clue that some author in Financial Times would read a mathematical paper, saying that we explained the so-called oil war in March 2020. And in April 2020, negative prices were observed. So those are rare events, clearly. And since then we felt that maybe this model was not stupid, completely stupid, and we did publish it and so on. So, okay, this is just one example, because I think everybody can follow at least this example. As usual, a real applied project, here it was on oil and so on, is a lot of work. It requires a team, it requires some time, it's not something you do overnight. So you cannot really do so many of those. Okay, let me switch on, and sorry for those who attended the workshop, because there is going to be here a few minutes, and then I'll be done. Okay. I just wanted to hear. So again, and now I'm going to emphasize the applications. This is a classical field in mathematics and physics, large random matrices. I'm mentioning Bishop, statisticians in 1928, and physicists there know well the semi-circular law of Wigner in the 50s, and Dyson work in 62. Okay, because of telecom applications, we were at that time, our team was being subsidized for public research by Huawei, and Merwan Deba was the head of research in Huawei, France, which was in fact very impressive, because I knew the guy, and the first time I saw him, he told me, I'm building a new research facility for Huawei in Paris. 2 years later, he had hired 70 people with PhDs from all over the world. I mean, that was very impressive, and some of them were pretty good. But anyway, so he mentioned to us, with mobile telecommunication, random matrices, maybe you should look into it, and so on. We also knew this field of random matrices as occurring in finance, just because that's the statistics origin of such problems, let's say by Bishop. You are collecting things that appear like random data. You look at the correlation matrix. If they are completely randomly independent, the spectrum of those matrices will be organized by a Wigner law. Okay? So if there are dependencies, which can be very important in terms of financial engineering, you see that you will have discrepancies, and then you have to understand what are the possible correlations and so on. In practice, you see not only the semicircular spectrum, but you also see spikes, which are meaningful both at the level of telecommunications and the level of finance. Okay, so because of telecommunication application, not so much finance, also there are hedge funds. There is a very well-known hedge fund in France which is essentially working on random matrices, and Simon's, the famous Renaissance hedge fund, a large part of activities was related to random matrices. Anyway, so it's getting late. I'm going to shorten this, and plus the fact that my friends, my friends and colleagues here have already listened to a more detailed version of that. So this is just the background. It turns out that what you're interested in, and that's the only thing I'm going to say, It's, you have a big matrix which is random. You're interested in spectrum. It's a symmetric matrix, so you have real eigenvalues. The spectrum, the eigenvalues. Number of eigenvalues is going to infinity because the size of the matrix is going to infinity. And again, what you look at is a so-called empirical measure, this sum 1 over n, sum of the delta ln I. So you are representing the state of the spectrum by a probability measure, again, like in min-field games. It has nothing to do with min-field games. Huh? It's just a mathematical. So then, as is well known, this is classical, you have an equation. But then, if you're interested in a practical situation like telecom, you want to optimize the system, okay? To make it as efficient as possible. And so this means that you have now this PD in the space of measure, and you want to control it. Okay, which means that you're led to write a Hamilton-Jacobi-Bellman equation on the space of measures. So this is getting very, very abstract, but I wanted to say that no one would have attempted to do so if there had not been the min-field games theory, which allowed us, as von Neumann said, to get used to write partial differential equations in probability space. So all those problems are indeed solved now, and you see what I'm saying, that although it has nothing to do with LFG, it has been made possible because we need it for practical applications, for creating this toolbox, which are the min-field games. We needed to introduce new mathematical objects, which then allow to tackle other applications, and that's an example of a feedback tool. Now, as usual in optimal decision theory, there are reality check issues. Okay? Let me take an example. This is a very classical debate in economics and so on. Take a billiard, a guy who plays billiard, okay, snooker. Clearly, he's not trying to look at the Hamilton-Jacobi-Bellman. He's not solving the Hamilton-Jacobi-Bellman equation to make the best possible move in order to win the game, right? Now, Bob Lucas, the same guy, said, well, this is not the right question, because the guy has played and played and played. He has practiced so many times. He has discovered practically the laws of reflection and all the effects, the twist, and so on. So in some sense, you have replaced the mathematical optimization by, it's not completely Monte Carlo simulation, but lots of experiments. Okay? And the end result is the same. So although it's not realistic to say that the billiard player is solving an optimal control problem, the result is the same, and that's what's important. I found this comment interesting. One can argue about it, but this is something which is all over the place in optimal decision theory. Of course, when you're dealing with robots and you have a fleet of robots and you want to control them and they interact, you're using min-field games, you don't have to worry about such philosophical considerations, but it's something. So I know that some people that are interested in biology are saying, well, the experience is evolution. I don't want to go there. I don't know. This is a different topic. So what I want to say is that this, by these comments, is that deciding about the efficiency of a mathematical model, about whether the model describes well the reality or not, is a little more complicated than it seems. Of course, you can check if the predictions are correct. Okay? For billiard, the curves are going to be the same. But there is more to it than what appears at first glance. But I guess that's a discussion for another evening, and you have been brave enough and patient enough first to listen all this time and to survive through this ordeal. So thank you very, very much, and again let me thank you, CPU, and all the staff that made our stay so pleasant. Thank you.
Thank you, Professor Lyons, for that insightful lecture. Now, we move on to the question and answer session facilitated by Professor Zheng Wang. May we invite Professor Wang to come to the stage. Professor Wang, please.
Thank you, Professor Lyons, for a wonderful presentation. Although I cannot even quantify how much percentage of the content I have understood.
I hope it's not zero.
I felt very inspired. As President Freddie Boyle said earlier, that's the most important part of coming to a presentation, right? So now the floor is open for questions. Okay, so the brave gentleman over there.
No, don't worry. Probably to all questions, my answer will be, I don't know. So go ahead.
But I'm curious about something, and maybe you can share about your experience. Because most of the time, when we look at some like a decision-making problem in a complex system, from a not very like people like me, I don't have a very excellent math skill. So if you see those kind of problems, how do you know which kind of problem can be solved by mathematics, and which kind of problem need to build a model to simulate to get some simulated result? So I just want to say your experience,
Okay.
To share to us.
Makes perfect sense. A very good question, which is a tough one because it's not only about MFG, it's about take a very complex fluid, what can we hope to be able, a very complex polymer, and the extrusion of a polymer is still a very complicated question. There are books about researching the properties of polymers and so on. How can we know beforehand if a mathematical model can be efficient or not? That's true in all applications. If it's possible, or at least one can do that in general on a toy model, like simpler version of the model. Try your model, and if it looks okay, you may want to invest in a more complicated situation. I will never claim that mathematics is the only way to think about complex situations. Okay? Never. It works for some problems. One recipe is whenever you observe some kind of regularity in the data, you may say, well, there might be some kind of mathematical explanation. So physical laws, it's about finding essentially the same data. Okay? So then there might be a law lurking behind. But that's true even in social sciences, economy, and so on. So some regularity in the data. Now you have such complex systems that there is no, for instance, very complex system, our brain. I have no clue about intelligence, I'm sure. It's completely useless to understand what's going on in such a complex system as our brain. So this we know it beforehand. For some other problems we don't know beforehand, and sometimes one has to try. And people have done that. It's not only us, it's everybody over the centuries trying to write down systems of equations and so on. Honestly, I think the first PDE which was ever written was by Euler. Okay? It's debatable because one can think D'Alembert was first. with the propagation of waves in the vacuum, and especially in 1D. But Leonhard Euler wrote down the first models of fluid mechanics in 1755. Why? Because he was ordered a fountain. And at that time, that was the top of that was really the most complex things when he was dealing with. That's why someone like Saint-Venant observed chaos theory in pipes in the Chateau de Versailles, 2 centuries before anyone discovered that in differential systems. So this was the top, the very complicated engineering. Honestly, when Euler wrote down the Euler equations, said, well, I think it's okay from a mechanical point of view, but there seems to remain a slight analytical difficulty. Okay? Two centuries and a half later, we are still having a slight analytical difficulty with the equations. Did he know that the equations would be relevant for the problem? He couldn't be sure. In fact, it was not true, because there was no viscosity, and there was one had, and it took about 50 years, and Navier, and with some help from Stokes, to write down the proper system of equations. So you see, there is an element of bet in creating a model. You can make some correlations with what you observe, and hope for the best. And some problems are not, at least in the near future, tractable by mathematical models and equations. No rule is the answer.